Okay, so the topic for today is digital inputs and outputs. Okay. Okay, so recalling from the last class, we are going to use a microcontroller. The microcontroller is called Atmega 328P, and it's mounted in a board that, in conjunction with the compiler, the software, it's called an Arduino, right? And we have some pins in the Arduino. Some are power. We have power pins, right? We have here 5 volts to power up other things, 3.3 volts, and grounds for reference those voltages, right? I can also supply voltage to the Arduino via the B pin or via this port, right? And we have a lot of digital inputs and outputs, right? Here I have 6 digital inputs or outputs, and here I have 40, right? So in total we have 20 of those. One of those have different properties, right? These 6 are also analog inputs. The one with the little symbol here can work as analog output, right? So those are other functions. We're going to study that in our class. Right now, I'm interested in the digital inputs and outputs, right? When you connect one of those, just be careful, try to not connect in D0 or D1, right? Because those are used for communication. So every time you load up a program to the Arduino, some information is passed through here, right? So if you have some high impedance element connected there, maybe the communication will fail and you will not be able to program that, right? And the correct procedure to do that is disconnect whatever it has here, upload the program, and then reconnect that. So we have other 18 ports, right? So these 2 are our last results, right? Will be our last result. First, we have this, what? Then we have this. And we'll have this in second place because these are really important because are the ones that can with analysis, right? But today we're going to study digital inputs and outputs. Any question? This point? Okay, so the topic for today is just to know how do we tell the Arduino that we want to work with a pin as an input or as an output, right? That's related to the homework, right? Did you finish the homework? Okay, if someone didn't finish the homework, I will reopen it until tomorrow midnight, okay? So you have a little more time to finish. If you upload something that is wrong, you can correct it and re-upload it in the same place, right? You have that extra time.
Mister, can we check like after?
We are going to check it in the class. That's my next step.
No, but like in this class, when it's over, can I go to you and check if everything is right?
Yes, we can. But we're going to talk about that here, so maybe it's not necessary, right? But yes, we can. Okay, so what was the exercise that I asked you to solve? A button, right? We want to do what with the button? We have to press the button, and the LED should turn on or off. We don't know what. Yeah. Anyone?
I could not download the software. The visual.
Yes, it's dead, right? You tried to download it yesterday.
No, I didn't.
When?
No, it was like over the weekend. I tried to download it.
This week. Yes. Yes. We have the second option. I am asking to tech services why it's not working, but in the meantime we have like Tech Digital Labs, right, in Canvas. You could use that in the meantime, right? Yes. Any more questions? Okay. So the problem states that we have to read a button connected to which pin? To pin 2, right? Then we have to store the reading value to one variable, right? And we have to write the value of that variable to an LED, to pin connected to pin what? Pin 3, right? Okay. So this is a solution, a possible solution for the code. Let me drop down this thing. The presentation is already on Canvas, right? So you can follow that because the projector is really dim. I already asked them to check it. It's still dim. Okay. So this is one solution. It's not the optimal solution. It's a solution that helps me to explain some little things, right? So we can start. Uh, we have our two main functions, setup and loop. Those should be always in our Arduino code. But I just start with these three lines, okay? The first two are a define line. The hash define is instruction to declare some constant value, right? So if you remember from the last class, I told you that the constant should be in capital letters, right? In number. So I am defining a constant called bottom with a value of 2, okay? Another way to define that is a line something like const int and then the name of the constant. In this case, it can be like that. And then equal 3, right? 2. That's kind of the same. Okay. The difference is that in this syntaxis, the compiler is the one that will be translating every time this word appears. So we don't need to put more power in the microprocessor, right? It's already changed for the microprocessor. So this is preferred for the Arduino, right? In our microcontrollers, it's not preferred. For the Arduino Uno, it's preferred to use this because we drop out some processing from. Okay. So this line just makes that the compiler every time the word button appears right here and right here, it automatically changes to the value 2. Okay. I have another constant called LED, and LED is assigned with 3. So every time appears the word LED, the program will put that with them. So this is just to make readable the code, but it will change once I am compiling the thing. Then I have this thing. This thing it's a variable declaration, right? So if I put just this thing, I am just declaring a variable called state, right? I am using common case, but it's just one word, so it's always lowercase. And it's the type bool. Anyone knows what's bool? Yeah, it's a kind of variable of boolean, right? Boolean. That is just 1 bit, right? 1 bit, and that bit can have 2 values, 0 or 1, just 2 values, right? What other type size of variables do you know? Float. Integer, right? String. Float. Float. That is kind of the same as double. We have char. Char is 8 bits, right? And we have others, okay? Right now, I am using a boolean because I just want to keep the state of the button. So in the button, I can just have 2 states, right? In the Arduino, in reality, I am not using just 1 bit. I am using 8 because I cannot assign just 1 bit to a variable. So even if I put here a boolean, it occupies 8 spaces. So I will be changing just this bit. Okay, the other ones will be unused. I keep that syntaxis because maybe I will use this code in another microcontroller with more power, and then I can use just 1 bit and I occupy less memory, right? In this, it's the same if I call this boolean or char because both of them are 8 bits, right? But it's fine. So I am declaring a variable called state, and I am initializing that variable, right? If I have 1 equal sign, it means that I am assigning the value 0 to that variable. So I declare and initialize a variable called state. Any questions up to that point? Okay. Then I have the setup, right? With some instructions. I will review this in the next slide. So I will jump this instruction. Then I have this thing here, right? So I am assigning the state variable whatever thing I am reading in the bottom pin, right? So if I have 0 volts in the pin of the bottom, this will be the state will be 0. If I am reading 5 volts, the state will be 1. Right? And then I have an if statement. If the state is equal to 0, right? I have a double equal sign. That means that I am comparing both sides, right? It's not, I am not assigning a zero state, I am just comparing if this is equal to this, right? It's for comparison. Two. If this is true, then I will run this instruction. If it's false, I will read this, right? And in reality, I will run all the instructions between these curly braces. And for the else, all the instructions. The instruction is a digital write in P3, right? This thing. And if it's true, I will write high. If it's false, I will write low. And that will solve the code, right? Any questions? Anyone use another kind of programming to do that? How? What's the difference?
I directly wrote
The state variable, right? So, yes. Another solution is introducing the else statement. You can just write here all of this. Digital write LED, comma, state. And then if the state is 1, it will not. If the state is 0, it will turn not automatically, right? That's another solution. It's short, but I want you to know the else statement, right? Any other that have a different solution for whatever part? It's the same. Yes, it should be kind. Yes.
the button connected to the first, so it was always an I, so we could fit
Okay, so you have a configuration like this. You have your button, right?
Yeah.
Connected to 5 volts.
connected to the pin, and the pin was connected to 5 volts. You have,
Okay, let's imagine I have the Arduino there, right?
yes,
With pin 2, right?
yes,
Disconnected here.
yes, and to the pin 2, I also connected the 5 volts to a resistor.
Ah, okay, like that.
Yes. Yeah, and that way the pin is always at high, so you push it, it goes low.
Okay.
The values are.
Perfect. Perfect. I will explain that. Okay, perfect. So, if I want to use a digital pin in Arduino as an input or as an output, I have to use this function, right? Pin mode. I declare for each pin, I put the number there, right? Pin 1, I want to use it as an input, or as an output, right? It depends on how I want to use it. I have 2 instructions for input. Is that true?
Yes.
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 I have one that is just input, and the other one is input pull up. Okay? It can be just an input or an input pull up. Okay? I will explain the reason for that. Okay? All right? So, imagine that I want to connect, again, I have my Arduino. It's connected to pin 2. And I put here my button because I want to connect a button. And I will begin with voltage source here. Okay. So if I press that button, what will be the voltage that I am reading in pin 2? So if I press the button, now it's like this, right? Okay, I'm reading 5 volts, right? 5 volts when pressed. Now, if I release the button, what will be the voltage plug here?
0.
0. Okay, 0. Are you sure? No, that's not true. Okay?
No.
Okay. Eh?
Yes,
It's reading electromagnetic noise, right? Okay. If I connect like this, what happens if I press the button? What will be the voltage in pin 2? 0, right? This is ground. So when I press this, I will get here 0 volts, right? If I release the button, like that, what will be the voltage here? Something weird, right? Okay, but I don't want that, right? When I lift this, we call this a floated pin because it's floating in the air, right? And it's kind of an antenna. So it's reading electromagnetic noise, our Wi-Fi signal, the electric signal. So this will be changing its voltage, right? It's neither 0 nor 5 volts, right? It's a changing value. So that's an undesired behavior, right? because I want to have two states, pressed and not pressed. Right now, when it's not pressed, this could tell me that it's pressed or not. We don't know. Okay? So one solution for that is to connect here 5 volts. Like that. Now, if the button is released, what's the voltage here? If it's like that. 5, no? I have 5 volts here, so the voltage in between is okay. And if I press the button, 0, but be careful, because now I have 0 volts connected to 5 volts, and that's a short circuit, right? You will see sparks flying everywhere. Yeah. I have to put something there. The solution is to put there a resistor. Okay? Now, if it's not pressed, the voltage here is 0, right? The voltage in this node is 5 volts. And the voltage here, what's the voltage here? No?
The sum must be equal.
Okay. What will be the current flowing here? The voltage across the resistor? I would draw like that, no? Right now I have here 5 volts, and here I don't have anything, right? Here is pin 2. Okay, so what will be the current flowing there? I don't have any ground, right? So this current is not flowing. So the current here is equal to 0. Okay, that means if the current here is 0, it means that the voltage here should be the same as here, right? That's the only way we can have 0 current. Yes? So when I put this, I have here 5 volts. Even if I have here a resistor, right? Because there is no current flow. Okay, good. And if I press the button, like this, now I have 0 volts, the pin will be reading 0, right? And here I will have 0 and 5, so I will have some current flowing across the resistor without any break. So now I have 2 states, right? Everyone's agrees with that? Okay, perfect. For the other configuration, let's imagine I put here my power supply. And I put on like that. When it's disconnected, I want to read here ground, right? So now I have 0 when it's released. If I press, I have a short circuit. So what do I need here? A resistor again, right? Now I will be reading ground when it's unpressed, and when I press it, I have the 5 volts, right? This resistor, when it's connected to ground, it's called a pull-down resistor because it's pulling the value of this floating cable to ground, okay? So that's called pull-down. In the other configuration, when the resistor is connected to 5 volts, it's called, how do you think it's called? A pull-up resistor because it's pulling the floating pin up to the voltage, right? So in this case, it's a pull-down. Okay, perfect. What do you think is the correct value for this resistor? Because the resistors have different values, right? Yes, everyone agrees on that, right? Okay. So let's imagine I press the button, I will have 5 volts in this side of the resistor, right? And ground in this side. Let's imagine that I have a resistor of 1 ohm. What will be the current flowing across that resistor? 5? 5 what? 5 amps, right? Why? Because according to Ohm's law, the current will be the voltage across the resistor over the resistor value. I have 5 volts across this resistor. 5 minus 0 is 5. Across its value, 1 ohm, I will get 5 amps. 5 amps is a lot of current, right? An Arduino pin should manage around 15 millis. So it's somewhat greater. If I do this thing with 1 ohm here, it automatically explodes. Okay, so that's a bad value. If I use 10 ohms, 10 ohms, what will be the current flow? 500 milliamps. That's still a lot. Okay, let's change it to 1 mega ohm. What happened there? Right now, the current will be really little, right? It will be like 5 microamps, right? Now the problem is that maybe I will not be reading the voltage, the correct voltage there, because the current is so little that maybe this pin is not capable to read that. So normally we use a value of 10K. 10 kilo ohms is like a middle ground, right? And that's the reason when you buy some cheap kits, it have a lot of the resistors, because with those we can do pull-ups and pull-downs, right? In reality, we could use values around 4 kilos, greater than 4 kilos, and smaller than 20K, right? Those are safe values to get our pull-ups or pull-downs, right? Use 10K, please. So everyone knows that's the correct value for pull-down. Any questions up to this point? Okay, all this explanation is because here I have one instruction called input pull-up. Okay, so that's really useful because, for example, here, if I want to read this, I have to declare this just as an input, right? But if I don't want to connect any resistor, I can connect my button directly to ground and then use the instruction pin mode into input pull-up. That will connect internally here a pull-up resistor. So I don't have to connect anything now, right? That's really useful if I have like 10 buttons I'd like to connect. I need to connect 10 resistors. In order to connect this thing, I have to declare the pull-up part of it. In this microcontroller, we don't have pull-down, but other microcontrollers have, right? We can declare input pull-up, and input pull-down. For this case, we don't have the pull-down. If you need to use the pull-down, you have to connect it physically, right? What do you think that can happen if I use the input pull-up and also put a pull-up here? I have double pull-up, right? What happened? How are these two connected? In series? In parallel, right? So the value of the resistor will be half of the real value, right? So if both of them are 10K, in reality I will have 5K. Yes. So maybe that's not good. Okay. So if you use input pull-up, this instruction, make sure that you don't connect anything externally, right? If you connect it externally, just use the input instruction, right? Without the pull-up part. Is that clear? Are you sure? Okay, because it breaks when you have a lot of things connected, it stops working for things like this, right? So it's really important. Okay, now if I declare my pin mode as an input or input pull-up, I can perform this function there. It's called digital read, right? Digital read goes to the specified pin and retrieves the value, right? 0 if I have 0 volts, 1 if I have 5 volts, right? If I declare my pin as an output, I can write voltage values here. With the state high, I will write 5 volts. With the state low, I will write 0 volts there, right? High is the same as writing a 1. Low is the same as writing a 0, right? So you can do whatever thing you prefer. Put here a 1 or write high or write a 0 or write low. Those are interchangeable. Is that clear? Sure. Yes, right? You use that in your homework. So now we are able to declare pins as an input, as an output, and write and read those pins. Now, in the code execution, we have those things. So I will now recall your first homework. What are the types of memory that we have in the Arduino? Which? Flash. We have flash memory. VRAM. EEPROM, right? Those are the three. SRAM, flash, and EEPROM. Okay. What's the flash for? The flash memory. What is used for in the Arduino? What is storing? No. Flash. Yes. In flash memory, we have our code. Is where we write all the instructions that we are going to run. Right. That microcontroller will run. Okay. Then the SRAM.
No problem. Well, don't think fast. Oh,
No.
follow instructions fast.
No, the SRAM is volatile. That's the one that does. The other two does that. Okay. Yes, it stores intermediate variables, right? So if I am performing an addition, in the middle it saves some values to do the operations. It's there. Also, we have registers that do specific things, right? They are also in the. It's the fast memory, right? It's really fast compared to the flash and the EEPROM. And the EEPROM is what's its main purpose? In there, you can write variables that you don't want to lose. Right? So you have to put some code there to store, for example, if I want to store the state value from the homework, right? I can store that, and if I reset it, and then I will have that value changed, right? That's not a correct use, right? Abundance will change. But for example, if I make a temperature control station that is really far, and I want to save all the history of measurements of the temperature, I have to store them in the EEPROM, right? Because maybe I will lose power and I will lose all my experiment, right? So I need to store the information in the EEPROM. The disadvantage is that the EEPROM just have certain number of writes and read cycles, right? That is really small compared to the flash. So in this class, I think we are not going to use the EEPROM. You could, right? But it's not necessary for any of our programs because we are not interested in check historical values. Okay, so this is like a diagram on how the microcontroller run the code, right? So I will start here. I have our program stored in the flash memory. It's written in lines, right? So we have all our code stored there. In which language stored in the flash? In Spanish, in English, in C++, in Percy, in which? In binary. So I would just have there zeros and ones, right? That are corresponding to some instructions. So the idea is that I will start from the first line. Yes, I use that to a special register called instruction register. So here I will have the current instruction that we want to run. Right? Then I have some part of the controller that will decode that. Right? So it will read like 0001. That means read pin 3. Okay. It will decode that. Right? And then we'll ask to the arithmetic logic unit to retrieve the needed value from the register. Right? This is our register, and the registers are in which memory? In the SRAM. All of this is in the SRAM. The flash is the one with the code, right? Okay. So with the code, we go here. I have a stack pointer, right? So the pointer is a number that is telling me in which row I am in the flash program, right? It's a stack because maybe I am reading here. I have to run a simple that is in another place. I have to do one pointer here and another here, right? Because eventually I will need to return here. And maybe I will enter in this function to another. So I will start having a stack of pointers, right? So I can return to the original code when I finish those functions. Then if I need, I can store some data memory. I increment my program counter and I run that second line. Right? Any questions? What's a register? Yes, I store things in the register, fine. But what's a register? It's a bit, it's 8 bits, it's a pin? No. It's a lot of pins? No. Those are a register is just space of memory, right? That has certain size. For the Arduino, no, all the registers, right here I have register 0, register 1, 2, I have a lot of registers. All of the registers are 8-bit length, right? So I have spaces with 8 bits that I can use for whatever thing, right? We have some special registers with special functions, and we're going to study some of them today, right? Any more questions? Is the flow of information kind of clear? It's really easy, right? And for us, it's not important because the microcontroller does that, right? It will be important if we need to do some weird special things to read, and we need to know where that happens, right? But it's not important. So we are going to study the use of registers. So that's a schematic of our microcontroller. This is from the data sheet of that Mega 328. So we have our CPU in which we process everything, and that CPU is connected to all the modules, internal modules, via the data bus. And you know what's a bus? A bus. This is a data bus. Yes, but no. Yes, it's like the road in which all the information will flow, right? So right here, our microcontroller, it's an 8-bit microcontroller. It means I have here 8 lines of data that will be shared between these modules, right? And also, I have another data bus here that is connected to the input and output. That's the reason I have a special data bus there. Remember, this is a microcontroller. If I just have a processor, I will just have this bus, but this is a microcontroller, so I will need to put information in the environment, right? That's the reason we have 2 buses. Some of the modules, I have the module for programming, the one that passes our code to the microcontroller. That is connected to a wire, so I can program some things, right? We have to do some operations for the microcontroller. That's not important right now. And it's also connected to the power management and clock control, right? So the CPU can decide which clock is using, how to move it. Also can control the power, right? It can pass power to wherever module it needs to work. Then we have the watchdog timer. The watchdog timer is the one that is checking that our microcontroller is running, right? If it gets stuck in one part, it will reset itself, right? Your computers have a watchdog timer, right? They have a lot. So if anytime you receive a blue screen of LED in Windows, you have received that. That's the watchdog timer, right? That checks, the graphics card is not responding in like 1 minute. We have to reset the system, and that's the reason it resets itself, right? The microcontroller has one, right? And that watchdog timer is connected to the module that is allowed to reset the microcontroller, right? To avoid the problem, right? Those problems occur because maybe we lost 1 bit of information and then you get stuck in something there. We have the analog digital converter that you can configure that. External interrupts, we're going to study that. I have the timer and counter 1, timer and counter 2. Here I have a timer and counter 0. This is special because it's connected to the inputs and the outputs. So I can count events externally from the microcontroller or count time external to the microcontroller. That's really useful. This is also the one that allows us to generate analog signals. These are the communication interfaces. This is the serial one. This is the one connected to pins 0 and 1. And this is the I2C. In this class, this is the important one, the input and output port, right? I have to be able to write and read information, right? It's done by this model. Right? Anyone knows what's a port? Port. Port. What's a port? It's not a connection.
Where do you connect?
Yes, you connect to a port, right? A USB port, whatever. But that's not the definition of port. A port is a collection of pins. Okay? So in the homework, you connect a button to pin 2, an LED to pin 3, right? A port is a collection of several pins, right? In a microcontroller, each port possesses 8 pins, right? So a port is a combination of 8 pins. How many ports do we have in the Mega? No. Okay, I will put the configuration. That's the configuration of that mega. How many ports do we have there? We have 28 pins, right? 28 pins. Some of those are for giving power, for connecting to ground. We have some pins that we use in the homework, PD2 and PD3, right? Okay. How many ports do we have? Ports. We have 28 pins, and ports are a group of pins. It should be less, right? We have just 3 ports in that arena. The ports are B, C, and D. That's the reason I have, for example, here PV. Let me go to PV0, PV0, PV1, PV2, PV3, PV4, PV5, PV6, PV7. Those are the 8 bits of port B, right? We have also port C, PC0, PC1, PC2, and port D, right? PD0, PD1, PD2, PD3, PD4, PD5, PD6, PD7, PD5, PD7, and those are the 8, right? 0 to 7. That is useful because those external pins are connected to a register, to a space of memory, right? So if that memory has zeros, it will be writing zeros. If that memory have ones, it will be writing ones, for example, right? If we use it as outputs. Is that clear? Yes. Okay. So we have 3 ports. Here, little is really little, but I have here PV, 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 PV. Those are the 3 ports. And I think that's important for that type. Yes.
PVs that that's like different amounts. For example, like PVC.
Yes.
Have like 6, and then like PV, like 1, 2, 3 have different amounts. Like, is there a logical?
Yeah, all of them should be 8, but I am missing which one? PD have 8, right? Also PV, but PC, how many we have there? We just have 6, right? It's because one of those is connected to the reset, so one of those is like a special use, and the other one is not present for us, right? It's just for the internal construction, so they are used for other things, right?
It's like a different name.
It exists, but it's connected to an internal thing that we cannot control, right? But if we have like infinite resources here in the circuit, they all will be 8. But we have 2 of 8 and 1 of 6, right? PV and PD are 8, and PV, in reality, the register is 8-bit long, but we can just have access to this 6, right? Yes, but it's just for space, the reason that we don't have. Okay, so those are the registers. That's the size of the memory. Which size is this? It's 2048 plus 160 plus 64 plus 30. I don't know what number is that, but that's the size of the SRAM in the Arduino, right? In that, we have some registers that are used to do the addition, the subtraction, that they are immediate registers, right? We can use it wherever we want. And then we have 64 of those that are connected to the digital inputs, outputs, timers, counters, to everything that we want to control. Then we have, again, the input and output. These are for special functions. For example, if I want to count a really, really big number, and the big number doesn't fit in the 8 bits of the register. So this, I can connect 4 of them to get a 32-bit register, right? In reality, there are 4 registers of 8 bits, but they are kind of connected in a way that is easier to run for that, right? So these are for more complex functions, right? And I have here more memory to write whatever thing I need, right? If I declare like 50 variables and I am updating them and I am writing all of them in an array, I need a lot of memory. I have that memory there, right? This is the number of registers and this is the size of the register. All the registers are 8-bit, right? Any questions? Okay. We are going to write code writing directly to the registers, right? And I am going to simulate that in Proteus, and I hope it works, right? Before that, Each one of the Arduino pins has those circuits. Okay. So this is pin, for example, pin 2, pin 3, whatever pin, and it has internally all of those things. Which of those elements you recognize there? Sorry?
Isn't the one on top of MOSFET?
Yes. Which one? This. Or no? This one? This one?
No, the
No.
one on the right.
This is the MOSFET. This is a MOSFET.
No.
Also, this thing is a MOSFET, right? A MOSFET is a transistor, right? And in this case, we are using the transistor as a switch. So this thing is the same as a button, but instead clicking it, we send a voltage and we activate that, or we send 0 volts and we deactivate that, right? It's a button controlled by voltage, right? So I have these two MOSFETs. Which other element do you recognize there?
Your ground.
A diode. Okay, ground. Yes, we have ground. Ground, right?
Resistors too.
Resistors. We have one resistor. Oh, perfect. What else? Logic gate. Which one? Okay, this one is what? The symbol is like this, right? That's an AND gate, right? So I have two inputs, input 1, input 2, output. I have 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1. What's the output for this?
0.
Okay, and it's a multiplication, right? 0 times 0, 0, 0 times 1, 0, 1 times 0, 0, 1 times 1, 1. We already know the truth table of the AND gate, right? In this case, this is connected to the right pin, right? It means that I can put here a 1 if I want to write information in the pin, or a 0 if I don't want to write information. If I have a 1 because I want to write and I put in the data bus a 1, I will have 1 and 1. What's the result of that? A 1. Oh, I will got a 1 here. If I put a 1 in the right permission, but I have a 0 in the data, what's the output of that? Here. So I get a 0 here, right? That's the, I'm jumping a lot of things, but that's the main functioning of that. Okay? And what other thing you recognize there?
The other logic gate.
Which one? This. Yes, that's an OR gate. The symbol is like that. 2 inputs, you can have whatever number, right? For this one, I have 2 inputs, 1 output. The possible values are 0, 0, 0, 1, 1, 0, 1, 1. And it's an addition, right? So 0 plus 0, 0, 0 plus 1, 1 plus 0, 1 plus 1. No, it's binary. 2 doesn't exist in binary. It's a 1, right? Because it's binary. Okay, perfect. So that's the truth table for the OR. What are the other things you recognize there? What's this? No. It's a NOT gate. So the symbol is like this. It has just one input, right? In, out. And the truth table is the negate of that, right? If I have a 0 in the input, it will return a 1 in the output. If I have a 1 in the input, it will return a 0 in the output. What other elements? I think those are the easy ones, right? The resistor, the MOSFET, the ground, these gates. This thing, it's called a buffer. The truth table for a buffer, it's really cute. If I have a 0, it returns a 0. If I have a 1, it returns a 1. So it is maybe unuseful, right? Because that's just a cable. The thing is that it disconnects the input and the output. So if I have a lot of noise here, it will not affect the thing before that. That's the reason it's called a buffer. It's separate thing, right? This thing, it's also a buffer, but it's a special one. That's the symbol for a Smith trigger. It means that it's a really fast buffer, right? Right now it's not interesting, but it will be interesting. So not buffer, the pin resistor. What this? That's an AND, right? But I have those dots here. You know what does that mean? It's the same as having a NOT. It's like the abbreviation for that. It just means that those are negated, right? But instead putting all the symbols, I know this signal PUD is negated. It's like a condensed form to write that, right? If you watch really close, the buffer with the little dot, it's just negated, right? The dot indicates that it's a negation. And what else? This little square, you know what's that? I will put one here. Q, block, and D. That's called a latch or a flip-flop. It depends on the clock, okay? It's like a memory. What it does is, if I have permission in the clock, it will pass whatever value I have here to the output. And then, if I don't have permission, I can change this, and it maintains the previous value. So it's just to store things, right? It can have different types of clocks. That's the reason this one doesn't have the little triangle, right? But that's for another class, not for today. So these are needed because this thing runs really, really fast. So I have to take like pictures of the data in certain moments to assign the values to everything. Right? All of this circuit is necessary because all the pins in that mega can be used as inputs and outputs, right? Before this technology, you have to find the correct microcontroller depending on your application. So if I need 20 outputs and 1 input, I need to buy the microcontroller that have 20 outputs and 1 input. If I need the other way, 10 inputs and 3 outputs, I need to find the one. With this technology, I just buy the correct number, like 23, and I declare the ones that I need in the mode that I need, right? And so all these circuits allow me to select if I want to use it as an input or as an output, and to move everything, right? Yes. Which is this one? It's a multiplexer. It changes, it selects this signal or this signal depending on this permission. So it's just like a button. You select which one will pass. This thing that is more complex is a valve. It allows the information to cross in this direction, but not to cross in the other one. It's like a complex diode there, but that's not something. Okay, that's the reason I don't explain in there. Okay, the thing that I want you to understand from this is that this circuit allows me to work with this pin as an input or as an output, and also with an input pull-up. Where do you think is the pull-up? This is the pull-up, okay? And I have this resistor connected to a transistor, and I can control if I let pass the current here or not. So it's the same as connecting or disconnecting the pull-up resistor. I control this with these signals, and the main one is this one. It's the pull-up disabled. So I can enable and disable this MOSFET, and that connect or disconnect, right? So if I write input pull-up, it activates this thing, and I have an internal pull-up. If I just put the input, it will disconnect this thing, and now I don't have the pull-up, right? So when you write that instruction, it will disconnect. Is that clear? Perfect. Now, to control all of this, I control that with 3 registers, okay? For each port, we have 3 registers. Yeah. I'm thinking I forgot my tablet to leave it in a file. I will try to draw it with the mouse, right? So don't be mad with me if I am not as good with that. Okay, so I have 3 registers. Let me. Okay, one register it's called DDR and X. Okay, let me put a lot of zoom here. DDRX. Then I have another one called port X. Port X. The X, we can change the X with B, C, and D. Okay, depending on which port we want to control, right? And the third one, it's called pin. Pin X. Okay. So what's the size of each register? What do you think is the size? Any guess? 8 bits. All the registers in the Arduino Uno are 8 bits, right? Always. Here, let me write once the space, and then I can copy and paste a lot. Let me try to draw it like this. Okay. 1, 2, 3, and 8. Okay. So I had 1, 2, 3 for each port, right? So for example, in the homework, which port do you use? You use 2 pins in the same port. What port was that? No. PD, right? We use PD2 and PD3. So those are pins in the D port, right? So these registers will be called DDR-D, port D, a pin, and pin D, right? If I want to control pin B, port B, all these should be B's or should be C's if I want to use port C, right? Okay, now this is called data direction register. What do you think it's for? DDR stands for data direction register. What do you think data direction? What it sounds? Any guess? Yes, it tells me about the direction of the data. Okay, so the direction can be an input or an output, right? So in that register, I can control. If I put a 0, I am telling that that pin should work as an input. If I put a 1, this pin should work as an output, right? This is connected to, let me, PD0. PD, let me write it with numbers. I think it's faster. PD0. This is like that, right? And this should be PD1, PD2, PD3. I will write here PD7. Those are my 8 pins. Okay, these are my 8 pins, right? It's 0, 1, 2, 3, 4, 5. If I write a 0, I am telling that PD0 is an input. If I want to use PD0 as an output, I should write here a 1, right? So right now, this is PD0, PD1, PD2 should be what in the homework? For the homework, what's PD2? Input or output? Input. So should be a 0, right? And LED in PD3, an output, right? I will write all this as outputs. So in reality, when I am writing in DDR, I am controlling 8 pins, right? In the same time, right? We are going to see the code later. Then, once I have declared my inputs and outputs, I use port D in the same way, PD0, PD1, PD2, PD3, PD4, PD5, PD6, PD7, to declare different things, right? If I have an input, for example, here, and I write a 0, I am telling no pull up, right? But if it's an input and I put a 1, it's with pull up, right? So with the combination of these two, I have an input without pull up and an input with pull up, right? Yes, is that clear? Now, if it's declared as an output, the value I put here is the value that I am writing here. For example, this means that I put for this one, for PD7, I declare as an output, I put pin mode output, and I am putting digital write 0 or low. And for this one, I have digital output, and I am writing a 1, right? So I can put whatever values I want to write there, right? Like that. Is that clear? Because it's not so easy. You have questions? Yes, this first one, it's called the least significant, and this is the most significant, right? The least significant is always connected to the 0. So this is PD0. This is PD1, PD2, PD3, PD4, PD5, PD6, and those are related to Arduino pins, right? So in the homework, we have PD2 connected to the button, is this one, and PD3 connected to the LED is this one, right? And it's the same for this register. This is the one for PD2, and this is the one for PD3, right? So we already know 2 of those registers, right? The third one is called port input. What's the usefulness for that? What do you think? To read the pins, right? So if I already declare one pin as an input, in this case, I will retrieve here the value. If I got 0 volts, I will be reading 0 here. If I am reading 5 volts in this other pin, that is the input, I will read here a 1, right? If it's an output, it's not important because I will be reading noise there. So this is just important for the ones that we already declare as an input, right?
What did you say 4D was for?
4D? Yes. 4D, if I declare as an input, and I put a 0, is without pull up. If it's an input with a 1, I put input with pull up. It's the same as writing input pull up. If it's an output, I am declaring as an output and writing a 0 in that pin, or as an output, writing a 1 in that pin. So it's already the digital write, right? So it's the same as putting digital write low, digital write high. Yes? So this is the complex one because it depends on the value of the data direction register, right?
And we don't do this like manually, right? We only have to write the code.
When you write the code with pin mode and that, you are moving these things. But the homework is to move these things directly. Okay? So it's really important that you understand that. Any questions? All with the ones are up, right? Here. If I put a 0, I am writing 0. And if I put a 1, I am writing a 1 in that order. I am giving 5 volts or 0 volts.
Yes, activating
Or activating that, right? 1 activates, 0 deactivates. If it's an input, 1 puts the pull up, 0 disconnects the pull up. Yes, the last one, if I declare this as an input, I will be reading whatever value connected here to this pin. So if I have 0 volts, it will be 5.
what is port? In like in card for input and DDR is the direction register.
Yes, it's just port. Yes, it's the register associated with port. Yes. It's because this information is written physically to that port. Yes, it's not an acronym. Yes. Any questions? Okay, I will show you how we codify that, right? How do I solve the homework? Doing those things. Let me. Okay. So here I have the information, right? In the that pin, 1 is an output, 0 is an input, right? Import, if it's an input, I connect and I give a 1, I connect the pull up, 0, I disconnect the pull up, right? And a pin is not here, right? But it's in the code. Okay, so let me return here. Here. Okay. What happened? Okay, this is a solution that I already showed you, right? The one in the left. I have two both, one in the left, one in the right. The one in the left we already studied. That's the solution I talked to you about in the first slide, right? This one is the same solution, but using the register. Okay? I'll explain line by line. The first thing is the declaration and initialization of the variable state. That's the same as this code, right? That should be clear, I think. Then I have my two functions and the loop. Right? In the setup, I am assigning to port D this number. I am talking about the register called port D, right? So the Arduino already know that I have that port, right? It's really important that I use that name and that I don't use that name for a variable, right? Because that's restrict variable. Do you know what means that thing? The 0B11110.
0B.
Perfect. Yes, it is. If I oh, almost. Okay. For example, I can write numbers here, right? This number is a decimal number. So I just write the decimal number. If I want to write in the state variable a 50, I can write a 50, right? Everyone's agrees on that? Okay. But in reality, whatever numbers I have here are translated to binary, right? So the microcontroller transforms that to binary. For example, these three, the microcontroller will just read this because it can just read binary, right? Okay. So if you write a number, the compiler, the computer, will think that that number is in decimal form, right? So if I write this without the 0B, it will think that this number is 11,011,111. And that's not the number, right? Because I am assigning that value in binary. So to indicate to the compiler that that number is in binary, I have to put the suffix 0B. So now the compiler knows that whatever number I will put here is in binary. It should be just zeros and ones, right? We have other suffix called 0x. That's for hexadecimal, right? So this is binary. Binary. This is hexadecimal. If I don't put anything, we know that this is decimal, right? And this is the one that you have to be really careful. We are not going to use that in class, but it's a common problem when you want advisories for other projects. Almost every time the problem that you have is that if you put the prefix 0, if you just write a 0 before whatever number, the compiler will think this is octal, right? That means that if you write 016, thinking that this is 16, it's not. It's 16 in octal, that is a different number, okay? So do not use leading zeros if you don't want to use it as an octal, right? That's the main lesson for this part. Okay, so here I am assigning to port D a binary number that should be how many bits to have that number? 8, because all the registers are 8 bits, right? If I just put 7 numbers here, it would be putting leading zeros, the order that we need, right? So we will move that to the lower. So in this case, I am putting 0B111. Why that number? Okay, I have one input in Bora, right? Is 2, is PD2, and LED should be an output in PD3, right? So if I count here, 0, 1, 2 is what? Sorry, I am working in this DDR, right? 0, 1, 2 is a 0, is because the bottom is an input, and this one is an output, right? For the other ones, you can put whatever number you want. Yeah? I decided to put all as an output. Right? In the comments, that's the reason I put X there, right? Because for this code, it doesn't matter. The only ones that matter are 2 as an input and 1 as an output. Yes?
In the port B, we have 111101. The only one that actually matters is the third one, because it's the one from bottom. So the numbers that we put on the other spaces don't matter?
Doesn't matter because I am not using it in reality, right? If I have things connected to those pins, then it's important to put in the correct things, right? Right now, I am thinking that you just have the button connected to 2 and the LED connected to 3. Yes? Okay, so with this, I assign the input and the output, right? Okay, perfect. And for 4D, I am just using it to put in pin 2 the 1 because I want to use the pull-up part, right? So I am generating the same code. Questions? Yes.
The output will always be the space to the left of the input. The space directly to the left.
No.
We have like PD2,
Yes.
it's 0, and to the left is 1. So it's the one in the left. But if we have a different input,
No, that's because we're using pins 2 and 3. If we connect the LED to 7, we should put this one as the up one, right? Because that's the right now it's because we're using 2 and 3. 2 and 3. Yes?
Yes.
And in this case, the pin 3, 0, 1, 2, 3, the value doesn't matter because I am writing to the LED and I will rewrite that really fast, right? Right now, I will start with the LED turned on. But if I want to start with the LED turned off, I should put here also a 0, right? Yes? Okay. Yes.
Or is the pull-up?
Yes, if it's an input, it works with as pull up or no pull up. If the pin is an output, you are writing that value.
And the DDR are
The one that declares if it's input or output. Yes? Okay. Any more questions about that? Okay, now this is my code to turn on the LED reading the button. Okay? So I am assigning the variable state this operation. Okay? I will break out that in parts so we can analyze that, right? What's pin D?
right?
Pin D, it's let me duplicate here. Okay, just let me quickly copy to have the code in the document. Snipping tool, new. I will bring these two things. Okay, and we are working there, right? Okay. What's pin D?
The reading.
Is the one that have the inputs, right? Okay, so I am taking that register and I am doing this operation. Greater than 2. Anyone knows what's that? This is called a right shift, right? So it's taking all these bits and I am going to shift two spaces in this case. This is that 7 number, I will move all the things 7. So let me copy this. I will copy Control C. Okay, perfect. No. Okay. Okay, perfect. So let's suppose that in pin I am reading pin D, right? I will write here pin D. And which bit is the button? This doesn't matter, right? Because this is an output, an output, an output, an output. Which one is important? 2, right? 0, 1, 2. This one is the important one, right? I will put like a little blob there. Because that could be a 1 or a 0 depending if I am pressing or not pressing the button, right? But it will be like that. Okay, that's the pin D. When I shift 2 to the right, I should copy all of this. Promise that I will not forget my tablet for the next. Okay, I have to do a right shift 2 times, right? So the little blob should move to the right 2 times. So this will be here 1, 2. So I will have the little blob there, right? This X should be here. This X should be here. This X should be here. Should be here. Should be here. This is this one, right? And these two, I don't know which value I should have there, right? Because I am shifting the specs. So those are unknowns, right? So this is pin D swapped 2 times to the right. Let me write pin D. Okay, now what's this thing? 0x01. Just the 0x01? What's the meaning of that thing? No? Anyone? What? No. It's a number in hexadecimal, right? Okay, you know hexadecimal? Yes. Oof, perfect. What's hexadecimal? No, you don't know. I see your face. Okay. Okay, so hexadecimal is a system that counts 16 values. That's the reason of the name. The values are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. That's 15, right? So from 0 to 15, I have 16 different values, right? Each of these values has the value in binary, right? So in order to represent 15, how many bits do you need in decimal? In binary, sorry. 4, right? So that's the 15, right? Everyone agrees on that? Okay, perfect. And for a 0, it's like that, right? And so this is 0, 0, 1. And let me 0, 0, 1, 0, and like that, right? So you will get up to that number. Yes? So here in hexadecimal, I am just dividing these 8 bits in 2 parts. In the first part, I have to represent a 0. How do you represent a 0 in binary?
0,
0, 0, 0, 0. That's this 0, right? That one here. And the 1? 0, 0, 0, 1. Yes, so if you want to represent a number in hexadecimal, you just divide in 4 bits, 4 bits, 4 bits. That's the reason it's really useful when you are programming, right? Because this is easier than remember all the number, right, in binary. Okay, so we have this part, we have this part. What's this? The ampersand. What operation it indicates? It's an and, yes? We are doing this operation. And we are doing that bit to bit. So it is not that I have to do that between this and this, this and this, this and this, the same bit with the same bit, right? Okay, so what's whatever number and 0? Whatever number and 0, what's the result for that? 0, why? Yes, because if I have here a 0 and 0, it's 0, and 1 and 0, it's also 0. So it doesn't matter the value, right? So I am just writing here 0. Whatever and 0, it's 0, right? Whatever and whatever, 0, 0, 0, 0, 0, right? Because every time one of the values is 0, I know already the output should be 0. And for this one, I have my bluff and 1. What's the result of that? If the bluff value is 0, what should I get here? And if it's 1, so it's the same as the bluff, right? So I will maintain my bluff here. Yes? What happened here? Okay. I read my register, right? I do the shift. I do the AND with this thing. This thing is called masking, right? When you delete all the bits and just maintain the one that you are interested in, all this operation is called a masking, right? Because you are just letting pass the bit that you are interested in. And I am saving this in state because now, if this bit is a 0, in state I will have which number? A 0, right? And if the state is 1, it's okay. This bit 1, in the state I will have a 1. So now I am just moving that. Yeah.
Why do we have to move the PD to blocks in terms of just zero?
Yes, yes, yes. That's another way to solve it, right? I can do the math and replace with the 4, right? And just let's pass it. The difference is that if I activate the word there, I will be reading a 4. So the state is going to be 0 or 4. In this way, it's 0 or 1. That is like more logical, right? But you can solve the problem doing the math without the shifting, right? And I am also using this to show what happens with the shift. Right? Okay, is that clear for everyone? Okay, so that's the thing. Now I have in the state of the P2 that is connected to a board, right? I now have that. Now we are going to analyze this thing. What is 0x F7? Yeah. 0x F7? Yes, it's an hexadecimal number, right? So I have to write with the first 4 bits the F and with the last 4 the 7, right? Let me just copy a bunch of this. Sorry? Yes. And then 0, 1, 1, 1, right? Okay, so this one should be the F is 1, 1, 1, 1, and the 7 is 0, 1, 1, 1, right? So that's 0 of 7. Then I am taking the state result, and I am shifting 3 times to the left, right? So if the greater than, it's shift to the right. This double greater, what's the contrary of greater than? Smaller than, right? If I have a double smaller one, is a left shift, right? So I am shifting the state. This is the state 3 times to the left, right? So here it should be 1, 2, 3. So I am moving this thing here, right? All these zeros are also moved 3 times. And these 3 things, I don't know which value, right? Because they were not in registers. Is that clear for everyone? Okay. Yes.
1, 1, 1, 0, 1.
This, okay. This is this number, the 0x F7, right? So with this, I know it's hexadecimal. So what I have to do is represent the F in the first 4 bits and the 7 in the second 4 bits, right? So the F is a 15. So here I have already that the F is 1, 1, 1, 1. That's the reason I put here in the first 4 spaces, those. That represents the F, right? And the 7 in binary is like that. This is 7, right? 6 was like that. 5 was like that, right? So I just look for the value and I write it here. That's the 7, right? So you just separate in 4 bits, right? If I have an hexadecimal that is, for example, FFE, I have to use 12 bits to represent that. We divide in groups of 4 bits, right? Okay. This is the shift. Now, what's this symbol? What? It's an OR. Yes. So I am doing a bit OR, right? Between these 2 registers, this and this, right? This is our number. This is the shift. So what's 1 or 0? 1, right? Then 1 or 0? 1, 1 or 0? 1, 1 or 0? 1, 1 and an unknown. 1 or 0 is 1, and 1 or 1 also 1. So it doesn't matter, right? If I have a 1 here, this should be also 1s, right? Now I have 0 or my blob. So if my blob is 0, the output should be a 0, right? And if my blob is a 1, the output should be a 1. So the value of the blob stays, right? So I will maintain whatever value here, right? Is that clear?
Sure.
Yes.
What is the difference between that and this?
Which?
Because I search for device,
Yes,
it's the same.
we use that.
So it's like 2 functions.
No, it's debit wise or I don't understand your question.
It's because it's like the same sign.
Yes, we are doing that. A bitwise OR. Bitwise means that we are attacking this bit by bit, right? So I look for the most significant bit and I do the OR with this and this, then this and this, and the output is here, this and this, and that means bitwise. And the OR, it just means that I am doing the OR. Or that was not the question. Yes, are you sure? Okay, yes. So here we do use the bitwise OR, and for this one was the bitwise AND, right? Those are the two functions that we use. This is the OR, the vertical bar. Okay, what do I achieve with this? Now the value of my button, right? I am putting in port D. So now I am writing that value, right? If my button is 1, I will write a 1 to the LED. If my button is 0, I will write a 0 in the LED. So I already achieved what I want, right? And all these things I left untouched. With the mask, I am maintaining the original values of the port D, right? So that's the reason my F7 number is just because I just want to attack the number with the 0 in the mask, right? I want to maintain this unchanged, the one that I use with the 1. Is that clear? Okay, perfect. So that's our code. And okay, perfect. So I declared inputs and outputs, right? In this case, I just declared the 2 as an input. I use a pull up for that input. I am writing a 0 to this output. All the other outputs are in 1. Then I am reading my register in which I just have connected the button to. I move that to the first position. I apply a mask just to check that bit. And I am sending that to the third position. That is the one in the LED, right? And this is to maintain all these values and change. All of this, I am just changing this bit. That is the so it's the same. It should do the same. Any questions? Okay, which of those codes you prefer? The left one, right? It's more readable for us. Which one you think is more efficient? The right one is so much efficient, right? The reason is because these functions, digital read, have to check all the ports. So every time you call this, it writes information to all the registers for all the ports. This thing, you are just changing the bit that you need, right? Another advantage is that you are going to see in the homework that in order to solve more complex problems, the code will be almost the same as this. And you are going to control for the homework 3 things, right? So that's another reason, right? If you want to control here 3 LEDs with 3 buttons, this code should be 3 times longer, right? So that's another way to see that. Sometimes when our code is really, really complex, we fill all the memory, right? All the SRAM. And the way to solve the capacity problem is to write all the code it is or some parts with this kind of code. And that will free some memory. We are going to be able to use the same microcontroller. We don't have to pay more to have more memory. Right? Okay. Now I will run this program in Proteus to check if in reality it runs, right? Because maybe I am lying to you. Before that, the homework is this. Click again, click. Why is not working? Let me. It's not freezed. Let me check. Okay, now it changed. Okay, the homework. We have 2 homeworks, right? The first one, you have to connect pins 2, 4, and 6 as digital inputs. So you have to connect a button to each one of those. And with those, you are going to control 3 LEDs, one connected to 3, one connected to 5, and one connected to 7, right? So the button in 2 should control the LED in 3, the button in 4 should connect the LED connected to 5, and the button in 6 should control the LED connected to 7, right? You have to generate the flowchart. So use Arduino instructions, the digital read, digital write pin modes, and solve it also using the 4 register, right? So you can generate your schematic, then save as, and then you upload one code to one file and the other code to the other, right? And you have to simulate both codes, and you write me if you notice some differences, right, between one and the other. Any questions about that? So you have to report both codes, the schematic, and the schematic is the same for both, right? Just one schematic, and the flowchart. That the flowchart is also the same, right? Because it's the same flow code. Is that clear? That's individual, right? So you should, yeah, before next class, okay? So it's for Thursday before 3 p.m. And you have a team activity that is to connect that in real life, right? So you have to implement that. So it's really easy. The code, you select the code that you love the more between the teammates. You should upload the one with the register. So you bring your code, your Arduino, and I will pass you by Teams at the beginning of the class, and I will check that it works, right? If it works, I give you all the points. If not, we check what happened, right? Any questions about that? Yes. We will check that at the beginning of the class. The individual part should be delivered before the class, right? Any questions? The spaces are not available yet. I will open those today, right? So just be careful with that. These instructions are already because the presentation is already uploaded. Any questions? Okay, let me put the code in the Arduino, open the Proteus, and we just upload that, right? Check. And I think I got it here. Okay, so now it's here. I don't know what happened there. And this is our Proteus, right? I will open our last file. I will use the same configuration, right? So it was that, right? Blink 607. That's our group number. I don't want to save this thing. Okay, so that's the exercise that we performed last class in which we have the blinking LED, right? So we have the power to the microcontroller. The reset is connected with this resistor to ground. What's the name of the resistor? Now you should know. Yes, it's a pull-down resistor, right? It's a resistor connected to ground. Its value is 10K. It should be a pull-down resistor, right? So this is connected to reset because I don't want this to be constantly resetting, right? If I want to do the manual reset, I can connect here a button to voltage, right? And when I press the button, it will reset, right? But I don't want to do that. And we have our crystal to generate the correct timing, right, for the microcontroller. Okay. For the code, do I need an LED connected to PC to PV5? No, right? I just need an LED connected to 3 and a button connected to 2, right? I will delete this thing, delete. Perfect. I will add a button. I will here place button. Button. Fine. I have already the code using the pull up, right? So I have to connect this to PD2, right? Because that's pin 2. And this should be connected to voltage or ground? To ground. Because I have the internal pull up in the code already, right? So this should be connected to ground. And do I need to connect here the pull up? No, because I already add that in the code, right? Perfect. And I have to add the LED, right? So place, I will use the same that I used last class. And let's rotate that. It's connected to PD3 with a resistor. I will ask you for that. Okay. The resistance value should be some value between 200 and 300. That's fine. And I will connect this here to voltage, right? Okay. If I do a digital write high to PD3, how is this LED will be? Off or on? Data right high. I will have 5 volts here, right? If I do. And sorry? No. No, it's fine. Okay. I will have 5 volts here, right? What's the voltage here? 5. So what will be the current flowing here? 0, right? Because I have the same voltage here. Okay, 0. So the LED will be off, right? If I don't have current flowing in the LED is not turning on. If I do data right low, the voltage here will be 5 volts, right? And the voltage here, 0 volts. So I will have some current flowing in this direction. The LED should turn on, right? So it can work like that. The difference is that now it turns on with the low and turns off with the high, right? Okay. I am just experimenting, right? The other way is just connecting the LED in the other direction and connect it to ground. That would be like the normal work, right? Okay. I have here the Arduino, right? I will put here the code. I think I got the code here somewhere. Here. That's the register code, right? Okay. I will save this file. Save. This is the same as the presentation. So I will call register let button 607. Right. Save. So now it's saving the file. How do I generate the code for Proteus?
Good.
Sketch. Fine. Export compile binary. And now the file is already generated, right? I have to go to Proteus, double click here. I need to look for the file. Right now, I have the one that is for the blink. I don't want to use that. I will return here. I have this one, right? Register let button 607. Build Arduino is the one from today at 4:44. Perfect. I have to use the one with bootloader, right? Because I want to convert this Atmega to an Arduino. I have to do this thing. Open. These things are already configured because it's the same file that we use. You just have to make sure that you have here on program the external full swing. These set fuses should be 10 and 16 megahertz, right? Now, if I run this code, I don't press the button. How's the LED? Why? Because I have the internal pull off, right? So this pin is connected to voltage. That's the reason I have the red square here. And I am sending the same to the P3, right? So I am sending 5 volts, and we already told that if I have 5 and 5, it should be turned on. If I press the button like this, now it's on, right? Because I press, I let pass ground here, I send ground here, and now the current is flowing. It works, right? And it's the register one. So you don't have excuses because now we know that we can write with registers, right? And it should work. Yes? Any questions? Okay, so that's almost all. The last thing, okay, for the homework that was for today, I will increase the delivery time for tomorrow midnight. And for your prototype, for the challenge, I will give you on Monday, right? You just have to bring your advances on Monday. So prepare for that. Okay? Do whatever work you need to do so you don't have anything. And the individual part for the homework that is in the presentation is before the class, and the group task should be already. Don't bring it to do here, right? It should be done when you come here, the physical circuit. It should be working. Okay? Fine, that's all. Thank you, guys. Yes.
The right.
It's good that you put it because in the real one, you should put that. Maybe in Proteus it's not necessary, right? If you already deliver the homework and it works, just put it for the next delivery. I will.
Similar, but I don't have the part in this part. I have like similar, but not exactly the same. But it works.
No, if it works, it's fine. But for the next one, I will ask you that every time you put the thing, it's a good practice, but that's the correct one. No, physically, you have all of those things already in the board. Just connect this part. Because the crystal and that is already in the board. Yes?
In the team, you have how many people?
Are the same from the challenge. Yes, the teams for the homework are the same teams for the challenge, right? Okay.